Hi, in this video we're continuing on from the previous ones where we got AOE comms running to allow Connect to talk to the drives over EtherCAT. We then configured and tuned the drive using Connect, and we'll continue working with the TwinCAT project and add all the necessary setup and software to get the PLC to control the drive and motor. So what we're aiming for is a simple motion setup where we'll be programming using the basic NC axis PLC open function blocks such as MC power, MC jog and MC reset. In terms of the hardware, we've got a laptop, it's got Control Techniques Connect loaded, it's got TwinCAT XAE shell loaded, and then we've got an Ethernet connection through to our back-off hardware, which in this case is an IPC, but it could be a controller or a PLC from back-off, it makes no difference. One of the ports has been configured for EtherCAT connectivity, and that is routed through to an SI EtherCAT, which is plugged into the drive that we're using, which is a Unidrive M700. Now, if you've got one of our dedicated servo products, such as Digitax HD M753, this interface for EtherCAT is built into the product itself. Now, even though these are separate and this is a plug-in module, you'll find that all of the steps that you'll follow within this demonstration are identical regardless of which drive or whether the interface is built in. So one last point before we get into it is that there's a user guide that follows along with this video and all of the other ones in the TwinCAT series, which is linked in the description. So there's no need to take notes, or if you just simply prefer to learn from step-by-step instructions, we've got you covered in the form of this user guide. Okay, so this is the basic project that we set up at the beginning, which has just the bare minimum setup that you need in order to be able to get ADS comms running and therefore get Connect to run. So I'll just run over that quickly just to catch up. So we've told the TwinCAT environment which target we're looking at by selection up here. I've then scanned for devices, found the EtherCAT interface on my IPC. I've then scanned for boxes, and then once we've found the boxes, I've said yes to add an NC axis. So we're now at the point where, if I just show you, there we go. So we've got our drive from a comms perspective, we've got our axis that is now connected to that, and now what we need to do is begin to set up our project. So the first step in doing that is actually adding a programming area. So we go add new item on top of PLC, standard project, and then I'm just going to reuse the same name as the project. So I'm going to add that, give it a little bit to sort itself out. So if I expand this, you can see all of the normal bits and bobs that you want to get a project working. So for example, here's our main program area, and here is our references. So this is the libraries that we're going to use in our project. So I'm going to double click on this, and we're going to go and add the libraries that are necessary for basic PLC open operation. Now, unfortunately, when you go and add the axis, it doesn't add these in by standard, so we're going to have to add them in manually. So I'm going to go add library, motion, PTP, and what we really want for basic motion is these two, MC2 and NC. So I'm going to add the first one. You can't add them as a block, you have to add them individually. So I'm just going to go and repeat that process. PTP, NC, there we go. So that's all of the libraries that we need in order to get very basic motion operational. Next thing that I'm going to do is make sure that the task rates are set to a sensible value. So by default they come in at 10 milliseconds, which is a bit slow. So I'm going to choose to up them to a more normal rate, which is a millisecond. There we go. So just make sure I've got all of them. There we go. Okay, so I think I've got all of the areas that we need to set up now. So the task time is set to something sensible. So next thing that we want to do is we want to go and add in the code that's required for basic operation. So I'm going to go and click on my main here. And let's begin. So the first thing that you need to do when you are adding a PLC open type axis is add an instance of axis ref. Okay. So I'm just going to add that. So axis 1, that'll be our instance name of type axis ref. Okay. So there we go. We'll link that in shortly to our axis here. So the next thing that we want to do is to be able to power the axis on, and to do that we use an MC power. So I'm going to call my instance of MC power axis 1 power. And it's of type MC power. Next thing that we want to do, I will just use a jogging function block, so MC jog, to be able to cause the axis to move. It's the simplest way just to get that sort of hello world moment of the axis turning. So axis 1 jog of type MC jog. And last of all, we're not necessarily going to use it in the demonstration, but it's certainly a good thing to have in any project, just in case you need to reset the NC axis, is to add in a reset. So that's what I'm going to do. Axis 1 reset MC reset. So this is not the same as a drive reset. This is simply resetting the axis in case you end up with some sort of implicit motion stop caused by limits or something like that on the axis. So there we go. That's all of the declaration done. So I'm just going to copy these very quickly down here. There we go. So first thing that you want to do, or the minimum that you need to do to be able to service the blocks and get motion working, is you need to connect its axis. You'll note that axis is of type var in out. All inputs of type var in out must be connected. Okay, so that's what we're going to do. So it's the input name is axis, and we are going to connect it to axis 1, which is our instance of axis ref here. And there we go. So that's that done. Now all I'm going to do, because it's the same requirement for all of these blocks, is copy and paste that down, and there we go. That's everything that we need to get our basic motion working. Axis ref, power, jog, reset, and then we've called them in our code. So next thing, we want to build that, and the reason why we're building at this stage and not later is because we want the instance of axis ref to appear as a selectable instance of a PLC open axis when we go and set up this axis here. So what you could see just before is that we've succeeded. There's no errors. Brilliant. Let's continue with the setup. So here is our axis. We've got settings. What you can see here is that when we scanned our network and we added our drive and we added the NC axis, what happened was it's connected for us drive 1, which is kind of the comms footprint of our drive, and it's already linked it into our axis. So there's no need to do that. It's already done for you. But the thing that we do have to do is we need to link it into the PLC code. So let's go and do that. And what you can see is axis 1, which is our instance of axis ref, is now available in the list. It wouldn't appear in this list if you had failed compilation or you'd forgotten to compile. So if you had an error and you compiled, it also wouldn't appear in this list even if you had compiled. But because we compiled successfully, it's there, it's selectable, we can go and add it. So next thing that we want to do is we want to go and configure our scaling, and the unit scaling, so that's the conversion between encoder counts that we see measured by the feedback device and units that we want to express distances and whatnot in at our axis, are housed within the encoder. So these are the two things that you need to work with. We've got the numerator and denominator for the scaling. So the numerator is the number of units, the denominator is the number of encoder counts for this number of units. So the best thing to do by far is just to normalize to revolutions, because normally you know the number of encoder counts per revolution of the feedback device that you got, which by default is 16-bit, which is 65536. And then the numerator is how many units that we've got for one rev. So we know how many encoder counts per one rev, we just need to know the number of units for one rev. And in my case, I've just got a pulley on the end of the shaft of this motor, so I'm just going to set it to an arbitrary value of 1000. Okay, you could be 360 if you wanted degrees. I'm choosing to use 1000. Next thing that you want to do, if you wanted to do some modulo movement within this one rev range because you're doing a carousel or some other rotary type application, you want to set your rotary rollover limit. So if you do like MC move modulo, this is where the modulo rollover is defined for you. So it's best to set it up at the beginning just in case whilst you're developing your machine you choose to want to use that. So there we go, that's everything that you need to set up as far as the encoder is concerned. Everything else is in the axis, so I'm going to choose the parameter tab, and the first thing that we want to set up is our maximum reference velocity and overall maximum velocity. Okay, these need to be set to whatever the maximum reference that our target drive will accept. So if we come back to Connect and then go to references, we can see that our maximum reference clamp is set to 3000 RPM. Okay, but if I come back to our TwinCAT setup, this value here is in units per second, so it's in our technical units, so that, you know, there's millimeters shown here. So let's say we've got 1000 millimeters per second, you know, or our scaling is for 1000. So we need to go and convert into our chosen units. Okay, so I'm just going to start up the calculator. This is just the Windows one, and we've got 3000 RPM, and we need to go from revolutions per minute to revolutions per second, because you can see the time order here is seconds. So there are 60 seconds per minute, so I'm going to divide that by 60, gives us a value of 50. We then need to multiply it by our number of units per rev. So this is revolutions per second, and we need to go to units per second. So we need to multiply this value now by 1000, which is our number of units per rev, giving us a value of 50,000. Okay, so we now know what our limit is. Type that in. Brilliant. Okay, so now we're not going to end up with any implicit stops by breaking this speed limit, and we're not going to be able to send a reference to our target that's any bigger than the reference that the drive will accept. So that's a good place. Next, you've got your acceleration limits. I would suggest to you that unless you've got a specific mechanical reason to limit the maximum acceleration, it's best to just put this out of the way, so that you can get your application working. And if you happen to want to put in an acceleration that's bigger than this number, it will work. Okay, so for me, I always set 2 to the power 20. Or so let's enter that. So it's 1 e plus 20. So that's a 1 with 20 zeros after it. This is the kind of magic happy place number for setting limits within LReal maths. So the actual biggest number you can do is 1e plus 30, but you'll probably find that 50% of the blocks in the NC Axis library treat 1e plus 30 as the maximum, but all of them treat 1e plus 20 as their maximum. So it's such a large number that under normal circumstances you should never come anywhere near it, and it would basically stop you from getting implicit stops caused by you putting, trying out an acceleration that was too big. So 1 plus E20, 1 E plus 20. I'll just copy that because I'll need that number again in a sec. There we go. So the last thing that I want to set up in terms of profiling is I'll actually set the default jerk to this big number as well. Now the reason I do that is that if you set 0 as the default jerk, what will happen is that it will automatically give you this very large number here. And when the jerk is set to an extremely large value, what it means is it will reach your maximum acceleration within one sample, which is the same as a linear acceleration profile, which is quite a handy thing to have. It's better than you having to sort of manually set this up to a very large number, just putting 0 in and you know that it's going to be linear. That's quite helpful. Next thing that we want to do, we want to turn off all of the native limiting, and it's simply because the values that are in there by default make no sense when you first set up an application. You've no idea what the normal following error is because you haven't tried it yet. So what I would suggest to you is turn all these off and then come back to this later if you feel that you need to give limiting for position lag, so following error, etc. But whilst you're trying to get the axis going in the first instance, you don't want the system giving you an implicit stop. So that's about it. We can now load this into the target. So we'll activate this configuration. So it's going to take all of these settings, push it into the IPC. Just click OK to all of the following messages, and we'll wait for our icon here to turn green, which we'll do in a sec. There we go. So now we know all that's gone in. It's confirmed by the fact that we can see that all of our values here are repeated in blue. So that's telling us that these settings have made it into the target. So next thing that we want to do is we want to go online, so then we can begin to tell our axis what to do. So what I'm going to do is I am going to enable the drive, which is applying 24 volts to the STO input of the drive. And I'll just show you at the moment, because TwinCAT hasn't been powered on, the drive is inhibited. Okay. Now what I'm going to do is I'm going to expand the axis power. And when you turn on axis power, what you actually want to do is turn on these three inputs. So we want to enable the block to be serviced, and we want to allow positive and negative motion all at the same time. So let's push that in. And I can hear that my drive is working, but that might not come through on the microphone, so I'll show you. Now the axis is in run, okay, so it's ready to accept our reference from our jog. So I'll come back, and then in fact, I'll put the camera on so that we can see. We are going to use our axis jog. So what I'm going to do is I'm just going to put some values in here. You don't need to set position, but what you do need to do is set the velocity. So I'm just going to stick 1,000 in here. Copy that. So it's going to get to 1,000 units per second in 1 second. So push that in, and then next all we've got to do in order to use it is tell it to jog forward. So there's a little bit of a delay on the camera, and there you go, jogging forward. I'll jog backwards as well. There we go. So I'll just stop that. So that's essentially everything to get that hello world moment. All of the setup, all of the libraries, all of the setup of the task times. Hope you found this useful. See you in the next video. Cheers.